Okay, so we mentioned, we talked about the torque. We talked about the angular momentum distribution, and we started from a tiny little ring, an infinitesimal ring of matter, where with angular momentum density times 2 pi r dr v phi times r. And we looked at the distribution of angular momentum with radius. Now let's think about the torque. So dl by dt, right, the rate at which the angular momentum changes with time is the torque. And so let's put torque. And so we have sigma r 2 pi r. Let's pull this out over here. We have v phi. We have another r, so let's put the r here. That's r squared. Oh, and then we have dr by dt. And so let's just write dr by dt is the radial velocity, or the radial component. So this is a vr. And so we can say, no, that's it. There's nothing to simplify there. Well, we can, let's just replace the constant. So 2 pi, the density, sigma, times, well, let's pull this further out because that's a function of, that could be a function of r. So we have a g mass of the black hole to the 1/2, and we have some density profile, which we could assume is constant. We did that just for illustrative purposes. We have the density, we have r to the 3/2 when we replace v phi, and then we have v of r. Right, so this radial inward radial velocity, the material is moving inward to lower values of angular momentum and lower values of energy. That's the result of some torque. So we haven't really specified what the torque is, but this is the result of that. Let's say the material flows inwards. We could construct an accretion rate, dm by dt, the rate at which mass flows in this accretion disk. This is equal to the density times 2 pi r, right, dr by dt. So we have v of r. Right, we did dr by dt. Well, we really started with dm, so we went back to the dm, and then we divided by dt, so we get a vr. And let's say that this is a constant. So there's a constant rate of accretion in the accretion disk. And so we can say that the radial velocity is some constant divided by 2 pi sigma r. And so the torque is, let's put this value of v of r in there. The torque would be r times v phi times a constant, which is some constant, let's call it a, r to the 1/2. And so we could get the torque as a function of radius, depending on our assumptions. So maybe we should remind ourselves of the energy for circular orbits for massive objects as a result of the gravitational force. We have kinetic energy, we have potential energy, minus gm. In this case, it would be due to the black hole over r, and overall this thing is some minus gm mass of the black hole over 2r. And so, right, the energy as a function of r looks like that. It's getting smaller. It's really these are all negative values. The most that it can be is when the object is at r equals infinity, and that gives us 0, right? So these are all negative values. It gets more and more negative the smaller r is, but the energy is decreasing, and so we've sort of played around with the equations. We haven't identified what the physical torque actually is. It just leads to this radial inflow velocity, lowering the angular momentum, lowering the energy, releasing that energy. And one assumes that all that energy is released because nothing happens to the structure of the disk. It continues on these ever smaller circular orbits. So here is the result of the radial inflow velocity, and that energy gets radiated away, and we observe bright accretion disks around black holes.